Okay, good morning, students. Today's topic is Avl tree. Okay, Avl, I will tell you what is the full form of this. Now, in our last lecture, we have discussed the binary search tree. So, Avl is also actually a binary search tree, but there is a difference between these two that would be clear. Okay, I okay. Suppose now I have to create a binary search tree. You have been given these elements for 3, 4, 6, 7, 9, 10, 11, 12, and 14. Okay. Now, if you have to create a binary search tree, the binary search tree would be like this. Because first of all, you are making a node tree. Next, you are inserting 4. 4 is greater than 3. So it would come to this side. Next is 6. 6 is greater than 3. Then greater than 4. It is coming to this side. Okay. So that is called the right skewed binary search tree. This is the thing, right skewed. Right means it is tilted towards the right side only. There is no node on the left side. Now suppose here if I want to search for whether 12 is there or not. Okay, like in binary search tree, I had told you what is the complexity to for the searching algorithm, that is big O of log n on an average. But suppose this is the worst case. What is the worst case complexity of this binary search now? Now, if I want to search for 12, how many comparisons I need? Just see. I'm comparing 12 with 3. 12 is greater than 3? Yes, you are coming to this. 12 is greater than 4. 12 is greater than 6, greater than 7, 9. So, one comparison, 2, 3, 4, 5, 6, 7, 8. So you need to do 8 comparisons in order to find out whether 12 is present there or not. So the complexity of this would be your big O of n. That means it would be linear. So it is not better than the linear search complexity. Okay. So your binary search tree would become just like your linear search. So in order to remove this disadvantage of this binary search tree, we are having now Avl tree. Avl. So what is the definition of that? This is important. This is a balanced binary search tree. Height balanced binary search tree. Okay. So what's the meaning of that? Balanced means the difference between the left subtree and the right subtree of any node, that should be balanced one. Okay, now what is the full form of this? It was introduced in the year 1962 by Adelson, Walensky, and E.M. Landis. Okay, so A is from that Adelson, V of AVL is from Walensky, and L is from the Landis. That is the full form of AVL tree. Okay, now what is the definition of that AVL tree? Now you take any binary search tree. Now when you can say that is balanced one, so that would be balanced if the difference between the height of the left and height of the right subtree is either 0 or -1 or +1. Okay, again I'm repeating it. You need to take the difference between the height of left subtree, here I have written height of left subtree, minus you say height of right subtree. If this difference is 0, then it is perfectly balanced. If it is -1, then also it is okay. If it is +1, then also it is okay. Like I'm taking one example. Suppose you take this tree, okay? You take this node first, okay? Now what is the left subtree of that? Left subtree of this node is this. What is the right subtree? Right subtree of this node is this one, okay? Now what is the height of the left subtree? Now how to find out the height of the left subtree? In the left subtree, you need to find out the longest path. Like the longest path I can say is this one. You are going to 20, then 10 to this node. Okay, how many nodes are there in that path? There are 1, 2, 3 nodes. So you can say the height of the left subtree is 3. Okay, now you take the right subtree. In the right subtree, what is the longest path? I can take this one, 36, 40, then going to 48. Now how many nodes are there in the right subtree? Okay, 3 in this path. So you can say the height of the right subtree is your 3. So what would be this is called the balance factor. What is the balance factor of this node? What is the height of left subtree? That is your 3 minus height of right subtree, that is also 3. So 3 minus 3, 0. So balance factor is 0. So that's why I have written 0 over here. So this is your 0. Like this way, I can find out the balance factor of any node. You take the balance factor of this 20. Okay. What is the left subtree of this 20? This one. What is the height of that? Two nodes in one path. So I can say 2. So this is your 2. Okay. Okay, now what is the right subtree of 20? That is this, only single node. So what is the height of that? That is 1. So what would be the balance factor? Balance factor will be height of left. First you need to write down height of left minus height of right. 2 minus 1, that is 1. So that's why 1 is written over here. Okay, next one more example I'm taking. You take this node. What is the height of the left subtree? There is no node. So what is the height? Height would be your 0. This is your 0. And what is the height of the right subtree? Single node, that is your 1. 1 minute. This is your 1. So 0 minus 1, so that is minus 1. So balance factor is minus 1. Okay. So this is firstly how to find out the balance factor of each node. You need to find out that. Okay. If balance factor is 0, node is said to be even high. Even high means height of the left and height of the right, that is even, balanced. Okay, that is equal. If balance factor is plus 1 would be if the left height is more than the right height. In that case, this is called your left high because the height of the left is more than that. But that is okay. Balance factor is plus 1, that is acceptable, okay, in Avl tree. And if the balance factor is minus 1, that means that is called the right high. Right high means in that case the height of the right subtree is 1 more than the height of the left subtree. Okay, so balance factor of plus 1, 0 or minus 1, these are acceptable. But if the balance factor is plus 2 or minus 2, that is more than this, then we need to make it balanced tree. That won't be a EVL tree. That would be a binary search tree, but that won't be a EVL tree. Okay. So I'm repeating the definition of EVL tree. First condition is that it should be a binary search tree. So before going through this topic, you need to go through the binary search tree topic, how to insert and how to delete. Otherwise, you can't do this EVL tree topic. Okay. So first condition is that AVL tree should be a binary search tree. Other thing is that while inserting and while deleting, we need to check the balance factor of each node. If the balance factor of each node is 0, 1 or minus 1, that is okay. We don't need to do anything. But if the balance factor is plus 2 or minus 2, then we need to make some rotations. We need to make some changes in that in order to make it a balanced one. Okay. So this is the thing that I had told you. Then in AVL tree, after performing some operations like whenever you will insert in your AVL tree here or whenever you have to delete some node, what happens then? The balancing factor of some node that may become 2 plus 2 or minus 2. In that case, we need to provide some rotations. Okay, so those rotations will balance this AVL tree. Okay, so I'm just going through this. In AVL tree, after performing the operations like insertion and deletion, we need to check the balance factor. If every node satisfies the balance factor condition, what is now that balance factor condition? That balance factor condition is that it can be plus 1, minus 1 or 0. Then we conclude the operation. That means then it's done. Otherwise we must make it balanced. Now in order to make the tree balanced, we need to provide some rotation operations. So rotation is the process of moving the nodes either to left or right to make the tree balanced. Okay. So I would be telling you in my next slides what are the rotation process. By using those rotation process, you can make your unbalanced tree a balanced one. Okay. So these are very important. So rotations can be of two types, single and the double. Single rotations are called LL, and the double are called LR and RL. Okay, all these things will be cleared once I would be taking some examples. So this is the thing that is important. First rotation that I'm taking is LL, that is called left of left. Okay, first I will tell you what is the meaning of that. Now suppose this binary search tree is this AVL tree is given to you. Obviously it is a binary search tree. This is an AVL also. Why? Because this is 20 and on the left side there is 18. Now what is the balancing factor of 18? 0. Why? Because the height of the left is 0, height of right is 0. Now what is the balancing factor of 20? What is the height of the left subtree? 1. Right? 0. So it would be plus 1 I have written. So this is an AVL tree. Now add 14. Now you have to add 14 just like you are adding in a binary search tree. Now start from this node. 14 is lesser than 20? Yes. Go to this side. 14 is lesser than 18? Yes. That means 14 will come over here. Fine? Okay. Now again after adding this, now this was your insertion. Again find out the balancing factor. What is the balancing factor of 14? 0. What is the balancing factor of 18? 1 minus 0 plus 1. What is the balancing factor of 20? Left side 2, height is 2, 1, 2. What is the height of right subtree? 0. So 2 minus 0 is your plus 2. So you are getting this nodes. This node is not balanced one. This is an imbalanced or unbalanced you can say. Okay, now I'm going to the previous slide. Just see, I had told you that while performing operations like insertion and deletion, okay, some of the nodes become imbalanced. Okay, so that is the thing that I have told you in this example. This is becoming imbalanced. Now we have to balance this. Okay, now how to do this thing? This is left of left. Why this is left of left? It is saying that subtree of a tree that is left high. That means this tree was already what? It was left high. Left high means the balancing factor was plus 1. But after adding a node, the subtree of that has also become left high. Just see. First subtree was even high, but now the subtree has become left high. Okay. So that's why this is called left of left. That means a tree that was already left high, after adding a node, the subtree of that has become left high. So in that case, what in order to make it balance, what you have to do, this out of balance node that you have to move towards the right side. Okay, now you assume that you are holding this node and you are making it down. You are rotating this towards the right side. So when you will rotate this towards the right side, it will become the right child of 18. Okay, because you are holding this, move it over here. So it is becoming right child of 18. Okay, now again this is a binary search tree because that is the first condition for AVL. Next, find out the balancing factor. Balancing factor of each node is 0. So this is your balanced tree. This was your imbalanced AVL. This is your balanced one. So which rotation we have done? LL. After applying LL, you are getting balanced one. So one more example I had taken. Suppose this is your tree. This is the balanced one. This is the balancing factor is plus 1, 0, 0, 0. Add 4 over here. Now 4 is lesser than this? Yes. 4 is lesser than 12? Yes. 4 is lesser than 8? Yes. So 4 is coming over here. After inserting this fourth node, find out the balancing factor of all the nodes. Okay. This is plus 2, plus 1, plus 1. So which node is imbalanced? This node. This node is imbalanced. So this is also left of left case because a subtree was left high. Okay, a tree was left high, but after adding a node, the subtree of that has also become left high. Like previously only 18 was left high, but after adding 4, the child node of that, this 112, has also become left high. So in that case, you have to move the imbalanced node, that is plus 2, the node having plus 2 balancing factor towards the right side. Now again, just see this one, how to move this to the right side. This is new one. Now hold this, move it like this, right side. So it would become the right child of 12. 18 would become right child of 12. 20 was the right child of 18, so it will remain same. 20 is the right child of 18. But previously, before moving, 14 was the right child of 12. So where it will go? It will become the left child of 18. Okay, so you are moving this towards the right side. So 18 is becoming right of 12. Whatever is the right child of this 12, that would become the left of this 18. Okay, so this is the left one. Again, find out the balancing factor of each node. You will be getting that it is either a 0 or either it is plus 1. Here also 0, 0, 0. So this is your balance tree. So this is your EVL one. So that was the first rotation, that is called your LL rotation. Next one is your RR. So similar to LL, but this is right of right. Okay. Now take this example 12, 18. So this is balanced one. What is the balancing factor of this? That would be 0 minus 1, because no node over here, one node. So this is your minus 1. So this is your right high. What is the balancing factor of this? 0. Now add 20 over here. So 20 is greater than 12? Yes. 20 is greater than 18? Yes. Just 20 is coming over here. Now again find out the balancing factor. This is 0, this is 0 minus 1. So left side no node, right side 2 nodes. So this is minus 2. So this is your imbalance. So this is called right of right. Why? Because we are saying the subtree of a tree. This tree was already right high, but after adding a node, this 20, this subtree has also become right high. Just see, it was previously 0, now it has become RH, right high. Okay, so this is right of right. In this case, in order to balance this type of tree, what is out of balance node? That is your 12. So this thing you need to move towards the left side. So you need to move this towards the left side. So 12 would become left child of 18. Okay. So this is still your binary search tree, because all the nodes towards the right side of 18 are greater than 18. Here this is lesser than 18, and even the balancing factor is 0. So this would become your balanced EVL tree. Okay, balanced binary search tree, that is called an EVL tree. So this is called right of right rotation. So these two are your single, because I had used only here right rotation, here left rotation. So these are called your single rotation. Next one is your double rotations. So this is your right of left. Okay, or simply you remember this thing. This is called LR rotation. Okay, LR means what now? Now take this note. Okay. So take this tree. This is your 12 and 4. What is the balancing factor of this? Plus 1. Balancing factor is 0. Now add 8 over here. 8 is lesser than this? Yes. 8 is greater than 4? Yes. So 8 would come to this side. Okay. Now again find out the balancing factor. What is the balancing factor? Here it is plus 2. Here it is now minus 1. And here it is 0. That means previously your tree was left high. It was left high. This L is from that left high. But after adding a node, the subtree of that tree has become right high. So this is right high now. Okay. Previously it was, if it was left, the subtree was becoming left high. If it was right high, subtree was becoming right high. But now it is opposite. If it is left high, the subtree is becoming right high, not the left one. Okay. So in this case, you need to provide two rotations, then only it would be balanced. What you have to do first is that this is LR rotation. Okay, again you assume that L is that first you need to move a node towards the left side. So which node would be moved to the left side? The subtree node that has become now left high. Now which node have become left high? Fourth. So I will move that towards the left side. Okay, move towards this to the left side. left one. So it would become the left child of 8. Okay, and 8 would obviously become the left child of 12. Okay, this is how to rotate this. You are holding this, rotate this one. So obviously this 4 is coming over here. So 4 would become left child of 8, and we have to put 8 at this place. So 8 is becoming the left child of 12. This is one rotation left L. Now R. R means now which node was out of balance? This node was out of balance. So move this towards the right side. Okay, when you will move this towards the right side, it will become right child of 8. So right child of 8. So this is your balance tree. Okay, so you need to remember if it is LR rotation, what's the meaning of that? That a tree that was previously left high, after adding a node, the subtree of that has become right high. Left, right. Okay, this was your left high, this has become right high. So rotation also you need to remember this. LR means first left and then right. Now this is just opposite of that. This was right of left. This is left of right. Oh, just remember this RL rotation. So RL means previously a tree was right high. After adding a node, the subtree would become left high. Okay. You take this node 12 and 44 is its child node. So 0 minus 1. What is the balancing factor of this? This is right high. This is 0. Now add a node 18. After adding a node, this has become now what? This has become left high. So tree was previously right high. The subtree of that has become left high. So RL rotation. For that again opposite of this, here you had provided first left rotation. Here it would be firstly R. R means right rotation. Okay. So here first you are doing the right rotation. So move this towards the right side. This node first, right side. So when you are moving this towards the right side, 44 would become the right child of 18. So 44 is becoming right child of 18 and 18 would become right child of 12. Okay, this is right R. Then L. L means the node that was your imbalanced node. This one, this you have to move towards the left side. So when you will move this towards the left side, so 12 would come over here. So this is your now balanced binary search tree that is called an Avl tree. Okay. So this is LR rotation. These are RL rotations. So four types of rotations we have done: LL, RR, LR, and RL. Now I would take one example. Mainly if the question is coming like this, write a note on Avl tree, then this much is actually enough. You need to write down the definition of Avl tree. What is the full form of that? What is a balancing factor? And then you can tell about all these four types of rotations. You can take one simple example the way I have taken. You can explain LL, RR, LR and RL rotations. Okay. Now I would be taking next one example. Suppose you have been asked that construct an Avl tree using the following nodes. Okay, the first thing is that you have to add the nodes in a similar way we have done in binary search tree, but here the difference is that while adding node you need to find out the balancing factor of each node. If the balancing factor is becoming plus 2 or minus 2, you need to provide rotations, either LL, RR, LR or RL, depending upon which type of rotation we need. Okay, so I'm taking this for 64, so I'm adding 64. Then is 1 is lesser than 64, so I'm adding over here. Now find out the balancing factor. What is the balancing factor of this? Plus 1, here 0, so it is already balanced. Now next is here 14. 14 is lesser than this, yes. 14 is greater than this, yes. So 14 would become the right child of this. Okay, so again find out the balancing factor. What is the balancing factor? Plus 2. But balancing factor of subtree is here minus 1. That means now which type of rotations I need in order to make it balance. Now what was the tree? Tree was previously left high. This tree was already left high. But after adding a node, its subtree has become right high. Okay, write down LR. So which type of rotation is that? LR rotation. So you can remember like this, LR. For LR, in order to balance this, firstly this subtree node you have to move towards the L side, left side, and then this towards the right side. So move towards this to the left side. So 1 would become left child of 14 and 14 would become left child of 64, and then you have to move out of balance node, that is this 64, towards the right side. Move towards this to the right side. Okay, 64, when you are moving towards right side, it is getting, you are getting like this. So this is your balanced one. Okay, now I would be using this and add next node, that is your 26. So 26 is greater than this, lesser than this. Find out the balancing factor. It is okay. -1 +1, that is acceptable. Next is 13. Add 13. 13 is lesser than 14, 13 is greater than 1. So it would come over here. Again, find out the balancing factor. It is perfect. It is EVL tree. 110, add 110. 110 would be added over here. Again, find out the balancing factor. It is either 0 or -1. Again, it is an EVL tree. Next is 98. Okay. 98, when you are adding, 98 is greater than this, greater than this, greater than this, lesser than this. Again, find out balancing factor. It is again, you don't need to anything because balancing factor is fine. Either -1 or 0. Now add 85. 85 is greater than 14, greater than 64, lesser than 98, lesser than 98. So 85 is coming over here. Now find out the balancing factor. So this is important for you now. Here it is 0, +1, +2, -2, 0, -2. So which nodes are out of order? This one, and this one. Okay. Now, how to make this a balanced one? Okay. You have to start from the leaf nodes. While starting from leaf node and going up, which node is becoming imbalanced? This one. So you need to consider this one. Okay. You don't consider these two nodes while starting from leaf nodes. You start from the bottom of the tree, go up. While going up, you will find out this node is imbalanced. Okay, so just consider this node. So previously this node was your left high. Just see, 110 was your left high, but after adding a node 85, the subtree of this tree has become right high. Just see, now 98 has become right high, and this was your left high. Okay, sorry, this is your left high. Your tree was left high, and after adding a node, even the subtree has become left high, not right high. This is left high only. This is +1. Okay, so which type of rotation is that? This is LL rotation. Okay, so in LL rotation it was very easy because this is a single rotation. What you have to do, find out the out of balance node. This is out of balance node, move this towards the right side. When you are moving this 110 towards the right side, it will become right child of 98. So 98, 110 is becoming right child of that. 85 was left. This is okay. And now, since 110 is coming over here, so 98 would become the right child of 64. So 98 would become right child. Now find out the balancing factor. It is perfectly balanced. That's why we don't need to consider these two. Okay, we need to consider this one only. So this is your tree from that list of element, and this is your AVL tree. Fine. So this is like how to insert the elements in tree. After adding the elements one by one, you need to consider the balancing factor. It is becoming out of balance, you need to balance this one. Next is the deletion in AVL tree. Okay, this is little bit different now. Now again, the actually it is very easy. Deletion is what? Now again, assume that you have been given this tree. This is the root node. Okay, and now you have to suppose delete any node x from this AVL tree. Okay, Now, after deletion of that, some of the nodes may have the balance factor of +2 or -2. We have to balance this thing. Suppose that node X is on the right subtree of A. It is somewhere over here. So when I will delete X, the height of this subtree will decrease by 1. If it is H, it will become H minus 1. Okay. Now after deleting that node, what I have to check? I have to check that which node, while going up, which node is having a balancing factor of +2 or -2. Suppose this node A is having a balancing factor of +2. Now here I deleted a node on the right side. So you go to the left side of this. The immediate subtree, the immediate left child of that I'm marking as B. Okay, you need to check whether the balancing factor of that is 0, 1 or -1. Okay, so what is the thing that I'm telling you? First thing is you need to check whenever you are deleting a node whether you are deleting from the right side or the left side of this subtree A. Okay, if you are deleting from the right subtree, then these are called R, otherwise these are called L. Okay, deletion is called R or it is called L rotation. Okay, R or L. Now it is on the right side right now, so it is called R rotation. Next, while going up, you need to check which node is having a balancing factor of +2 or -2. Now this node is having a balancing factor of +2. Go to the left child of that. This is the left child B. Now find out the balancing factor of this. If the balancing factor of this is 0, this is called R0 rotation. If it is 1, it is called R1. If it is -1, it is called R -1. Okay, I think I would take first one example, then it would be clear to you. You take this example. 1 minute. You take this example. This was your AVL tree before deletion. Now delete 60. When you are deleting this 60, how to delete this 60? This is again very important that you have to use the same method that we have done in binary search tree. Now this tree is not having any node, so it would get deleted and the right child of this 54 will become null. So this right of 54 is becoming null. After deletion of this, find out the balancing factor of each node. Okay, this is the balancing factor of each node: +2, 0, 0, -1. Now you had deleted this node, go up toward this side. Now which node is out of balance node? This is out of balance? No, this is out of balance. So mark this as A. This is your A. Okay, now we had deleted from the right side, so this is your right rotation. So I can write down R. Now this is your A node. What is the left child of that? That is your B. Mark this as B. Now what is the balancing factor of that? That is your 0. So this type of rotation is called R0 rotation. Okay. In this rotation, how to balance this one? What is your out of balance node? Out of balance node is your 46. If your rotations are R, whether it is R0 or R1 or R -1, it is very simple. You have to move your out of balance node towards the right side. Okay, move this 46 towards the right side. So when you are moving your 46 towards the right side, 46 will become the right child of 20. So 46 is the right child of 20. Okay, and this 54 will become the right child. It was right child of 46. It will remain same, but previously the 23 was the right child of 20. This, but now this 23 will become the left child because 46 is coming over here, so it will become the left child. All other things are going to remain same. Okay, so after the deletion you need to find out the rotations, whether this is R or L. Okay, okay, I'm taking one more example. You take this one. Suppose this is your AVL tree. Okay, now delete 39. This is 39. It again, it is not having any child. When you will delete this, the left of this will become null. So this is there. Again, find out the balancing factor. Again, the balancing factor is 0, +2, all these things. Okay, Now first thing is that you deleted from the left or right side of this root node. I deleted from the right side. So this is R rotation. Now after deleting this, go up over here. Which node is out of balance? This is out of balance? No, this is out of balance node. Mark this as A. Okay, now go to the left child of that. Mark that as B. What is the balancing factor of B? +1. So this is called R1 rotation. Okay, that's why it is written R1 rotation. Okay, again, actually the thing is same whether this is R0, R1 or R minus 1. What you have to do, which node is out of balance? Just find out the out of balance node and move towards this to the right side. Move towards the right side. So this is will be becoming the right of 26. So right of 26 is 37. Previously, whatever is the right child of 26, that will become the left child. Okay. So even if you don't want to remember this R0, R1 or R minus 1, what you need to remember after deletion of this, just find out of balance node. What is the out of balance node? +2. If you have deleted from the right side, then just rotate the out of balance node towards the right side. Okay, so that is done. And whenever you are deleting from the left side, find out the out of balance node, and that balance node will be moved towards the left side. Only difference is that. Okay, so I'm not doing this thing because this much is enough for you, that how to delete a node. It can be from the right side or it can be from the left side. So this is all about the AVL tree. So again, I'm repeating over here. This thing is important. What is the full form of this AVL, and what is the definition? What is this balancing factor? And you need to do all these rotations. So these are important. Okay, LL, RR, LR, and RL. So these examples you can do.